Hello everyone, and thanks for joining us today for the latest DDN webinar. My name is Yuning Wang, Associate Science Editor for DDN, and I'm here to moderate today's event. I'm very pleased to introduce our speaker, Kevin Lentz, who will be presenting the talk Uncover Aggregation ASAP for Proteins, Peptides, and ADCs on Stunner. Kevin covers the Stunner portfolio globally at Unchained Labs. His expertise includes biophysical characterization of proteins, nucleic acids, viral vectors, and lipid nanoparticles. Prior to Unchained Labs, his research experience covered the fields of sustained antibody delivery and nanotechnology. He earned his PhD in bioengineering from the Joint University of California, Berkeley, University of California, San Francisco Bioengineering Graduate Program. A very welcome to you, Kevin. We're very pleased to have you joining us today, and we look forward to your talk. To our audience, following the presentation, we'll have a Q&A session, and we welcome any questions you may have. Please ask questions using the Q&A system to the side of the live stream player. So without any further ado, I will now hand over to Kevin to begin his talk.
Hello everyone, thanks for joining my webinar today on Uncovering Aggregation ASAP for Proteins, Peptides, and ADCs on Stunner. I'm really into growing strawberries right now. It's the perfect season for it. Currently, my favorite kind is Mare de Bois, but when you're growing strawberries, lots can go wrong, like gray mold shown here. And if you're not on top of your game at detecting the problem and weeding those problems out, those problems can really derail a successful harvest. Working with biologics, peptides, and ADCs works kind of the same way. You have to keep an eye out for problems like aggregation and make sure they don't spread to the next assay or process step. If we're thinking about characterizing proteins and making sure our problems don't go on to the next assay or step, there's two questions I want to talk about today. The first, how much do I have? Simple quantification. If I'm thinking about quick checks on how much protein I have in a sample, usually I think about UV-Vis for protein quantification based on how much light is absorbed by the sample. The other question I want to talk about today is, do I have aggregates? In other words, making sure I don't send those aggregated proteins downstream to the next assay or process step. And when you're thinking about quick, easy, simple answers for aggregation on proteins, dynamic light scattering, or DLS, is the technique that fits the bill. This is going to give you answers on size and aggregation to make sure that your protein is exactly what you think it is and aggregates haven't struck. These are two great techniques, but it begs the question, since they're so great, can we combine them in a single assay? And the combination of UV-Vis and DLS is exactly what Stunner is. It's the only system that pulls together those two separate technologies to gather results on a single 2 microliter sample and give you those answers from DLS on sizing and aggregation and protein quantification from UV-Vis. And it will also now look at results on ADCs to give you answers on average DAR based on UV-Vis information. So that way you can run a single sample on Stunner, and without skipping a beat, you'll know if your protein sample is good to go in the next assay or process step. The secret of Stunner's success starts with the Stunner plate. It's laid out like a normal 96 well plate, but instead of each well where we load samples, we have a microfluidic circuit where you pipette in 2 microliters into that input well, and it gets wicked into the Stunner microfluidic circuit and read by the 2 microcuvettes. Once it's inside of the instrument, those microcuvettes are where the sample is read for UV-Vis and for DLS. This is a really handy way to characterize your sample because it's SBS format, so it works with automation, it works with multi-channel pipettes, it works with 96-channel pipette aids. Everything's ready to go, just like it would be in a 96 well plate. Here we can see exactly what sample loading looks like with the help of some fluorescein and a blacklight. In 2 wells, we've already added 2 microliters of fluorescein. And as you can see, shown in real time, to load another sample, you simply add in 2 microliters into that input well, and the sample wicks into the plate. On the left, you can see those loaded samples, and on the right, you can see the samples after being measured with Stunner. The 2 diamond shapes are the cuvettes for one sample, and what this shows is, after pumping, all of the sample remains in our consumable, so there's no contact between the sample and the pump system, there's no cross-contamination between one sample sitting on a pedestal and another sample sitting on a pedestal. It's all just read nicely in individual wells in a 96-well plate. The results for UV-Vis look something like this. So here we're looking at a dilution series of IgG going across a very wide dynamic range and being measured in octuplicate at each concentration point. So on the left, we could see each of these traces, but instead of seeing individual lines, we're actually seeing overlaid lines that you can't even tell are individually distinct. That's how precise the result is. The story is the same on the right, where we're graphing expected concentration versus A280. And again, we have 8 individual points for each of these concentrations, but the overlay is so precise that they look like a single data point. This just gives you an idea of how much concentration data you can get in that 96-well plate and how great throughput and linearity you can achieve it as well. Here we're quantifying that data a little bit further to show off known concentration versus measured concentration and demonstrating linearity very close to 1 with an R squared greater than 0.9999. And then for accuracy, we're comparing known concentration and average concentration on the right, along with %CV or RSD, to show that our accuracy is within 2% and precision is within 1%, thanks to the 2 fixed path lengths that we're reading UV-Vis data on. That gives us a wide dynamic range from having 2 path lengths, and the fixed part of it means that those results are very accurate and precise because there's no moving pieces in the critical light path. Here we're showing an example data side by side of an IgG being read in octuplicate on Stunner. What you can expect from this kind of read is a concentration data point from UV-Vis, in this case about 10.3 mg per mil with a CV of 0.2%. Again, we're showing all 8 reads overlaid by UV-Vis on that graph. And on the right, we're showing DLS data that indicates that this antibody is very nice and monodispersed with the Z average diameter exactly where we would expect it for an antibody at 11 nanometers, with again a very precise CV of 1.5%. And here's a look at some other sizing data from DLS to start to introduce a few more concepts from that measurement. So on the left, we're looking at intensity distributions where diameter is graphed versus Rayleigh ratio or scattering intensity, depending on how you like to think about it. So ovalbumin is a smaller protein and thyroglobulin is a larger protein. You could see that based on where those peaks fall on the x-axis. Again, we're showing triplicate reads that have been overlaid. Now, because ovalbumin is a smaller protein and these are being read at the same concentration in terms of mg per mil, there's less light scattered from ovalbumin and more light scattered from thyroglobulin. That's why those peaks are different amplitudes in the intensity distribution. However, the other output that a lot of folks use from DLS is a mass distribution, where we're graphing diameter versus the calculated mass density, or mg per mil, depending on how you want to think about it, for those peaks. In this case, because we know that we're measuring these reads at the same concentration based off of our experimental design and our UV-Vis data, the calculated mass distribution actually shows the amplitude of these peaks at the same height, matching the area under the curve and giving you very nice overlays of those triplicates. So what we can tell from these 2 graphs together is 1, how intensely do our particles scatter light? And 2, roughly how many of them are there? How big of a problem might aggregates be, in other words? In this case, we're seeing just 2 normal proteins. However, if we take that use case a little bit further, we can do a spike-in study to demonstrate the usefulness of this technique in detecting aggregates. In the left column, we see a nice, happy antibody sample that's pure and showing no aggregation present. But when we spike in a little bit of aggregates in these two graphs on the right, what we now see is intensity distributions that very easily show off that there's lots of aggregates present because they they scatter light very intensely. However, when we calculate that to a mass distribution, you can see that there's a very tiny peak there, indicating that these particles are a very small proportion of the overall mass of the sample. So all of a sudden in one read, we have the ability to detect very rare large particles, and we also have ability to understand approximately how big that issue is in our sample. If we want to start applying this to other use cases, we can take a look at formulation screens by DLS, where in our correct and optimized buffers, we can expect proteins to be monodispersed and ready to go to the next step of development or functional testing. But in the wrong buffer, we can start to see aggregation and indications that our proteins are unstable and really going to be problematic for our next assay or process step. Here we're showing a formulation screen of a monoclonal antibody at about 50 mg per mil in two different buffers, a commercial and an acidic citrate phosphate buffer at pH 4. You can see right away from the DLS intensity distributions, the protein is monodispersed in the commercial buffer, but aggregates in the other one. And we could do some quantification of that as well. So at the table at the bottom, we have a z-average diameter that shows that our weighted average diameter for our commercial buffer is much lower than our acidic buffer. Our PDI is below 0.1 for our commercial buffer, which is ideal. However, it's above 0.2 for our acidic buffer, indicating that we have a very polydispersed heterogeneous sample. And then we're also looking at the average size of our two peaks in our intensity distribution, giving us quantitative information on where those peaks occur. If we want to take formulation screening one step further, what we can do is use a KD-B22 assay to understand protein self-self interactions in different buffers. In this case, we're looking at an IgG and succinate buffer, graphed in green on both graphs, and an IgG and PBS, graphed in blue in both graphs. In this experiment, we're running a dilution series and measuring light scattering information. Static light scattering is used to create a B22 graph, and dynamic light scattering is used to create a KD graph. Note that this is KD, the diffusion interaction parameter, not binding coefficient. So in these graphs, what we're looking at is the slope of the lines. For the B22 and KD graph, the succinate buffer has a positive slope, which indicates repulsive self-self interactions, and the PBS line is near zero or negative in both cases. How we interpret this data goes something like this. As you increase the concentration, you are increasing the frequency of self-self interactions of your protein in its buffer. So as the frequency of self-self interactions increase, you start to change the behavior of your protein very slightly. If your protein ends up slowing down, in other words, the diffusion coefficient decreases, then that's like the protein being attracted to itself, kind of like the north-south poles of a magnet. If the diffusion coefficient increases, your protein's getting faster, and the protein's repulsive to itself, kind of like north-north poles of a magnet. That's desirable because it indicates that your protein is less likely to aggregate in the future. B22 works in a similar way, except it's being done on static light scattering instead of dynamic light scattering. So it's looking at a parameter that's closer to molecular weight than it is actual diffusion coefficient, which is related to speed of movement. We can also take these kinds of tools and look at peptides. So here we're studying semaglutide and liraglutide. We're actually looking at these GLP-1 receptor agonists in quadruplicate and again overlaying the UV-Vis results and seeing very, very nice, precise CVs for both of these reads. And because we can read both UV-Vis and DLS on Stunner, we can identify some of the aggregation behavior that peptides are famous for. So here we can see the sample freshly diluted in PBS, and because they're mostly stable at pH 4 and not pH 7, really quickly after about 15 minutes, we can see this sample begin to aggregate and detect those larger species in the intensity distribution, even though there's still a smaller proportion of the species by the mass distribution. That was a look at proteins and peptides. Now let's pivot and look at another set of problems that can strike another class of biomolecules, ADCs. For ADCs, analysis is similar to proteins and peptides, except much harder for UV-Vis. All of a sudden, answering the questions about how much do I have and what's my average DAR become way more complicated because we have a UV-Vis spectra that is way more complicated. Instead of just having one component represented in that spectra, now we have two, and analyzing it can be a lot more difficult. Thankfully, DLS still behaves the same way, so checking out if I have aggregates or if my sample is the right size is still pretty simple. The classic method of looking for DAR by UV-Vis looks something like this, where the important part is these equations here on the right. This is a system of equations that's solved simultaneously, and the idea is you measure absorbance at two wavelengths, and you input 4 extinction coefficients in there, and then voila, average DAR and concentration of your antibody and drug pop out of those equations. However, those 4 extinction coefficients that you need to run this system of equations can be really hard to figure out. Either you might, because the ADC molecule that you're working with might be novel and the drug linker may not be characterized in quite the right way for you to know those extinction coefficients, or there could be enough of an overlap between your drug spectra and your antibody spectra so that it becomes very problematic to try to measure those. It's because of those problems that we decided that UV-Vis needed more flexibility because you can see here an example where you have an overlapping spectra between your antibody and your drug, and determining those extinction coefficients can be total deal breakers to using that system of equations. That's why we developed ADC decode, which allows you to measure your ADC, in this case trastuzumab emtansine, and decode it so that you can get your antibody concentration, your drug linker spectra, all from knowing only your antibody spectra and just simply measuring your ADC. So in a simple experiment, I'm adding my ADC sample, hitting go, and Stunner is going to take the antibody spectra from its library and figure out how much antibody is present, how much drug linker is present, and if I know one extinction coefficient about my drug, how much drug is present and the DAR value from that ADC. So let's take a look at this application for 3 trastuzumab ADCs, emtansine, deruxtecan, and vedotin. For these molecules, if I read them by UV-Vis, I get these total gray spectra shown here at the top of the slide. But then when I apply the ADC decode application using the trastuzumab spectrum, I can all of a sudden extract out the drug linker spectra for each of these drug linkers. That's valuable because it helps me in future method development for understanding those drug linkers, but it also helps me understand right away the accurate concentration of my antibodies. If I do go ahead and analyze those drug linkers forward, in this case we're looking at 2 of those same trastuzumab derivatives and 1 narituximab derivative, because these are the ones that we were able to get DAR off of C of A documentation. We can evaluate extinction coefficients from literature versus C of A DARs and see that we have expected results within about 10% based on our analysis here. But we still might have a problem of not knowing our extinction coefficient. In this case, what Stunner will report is DAAR, or drug antibody absorbance ratio. In this case, we're just going to export the OD at the wavelength that you want for your antibody and your drug, and you can use this just like you would a normal DAR. It's going to be exactly proportional to a normal DAR, and it helps you make relative comparisons even about drug linkers where you have no prior knowledge related to extinction coefficient or concentration. Meaning that if you're screening molecules very early on, you can still get information out of them that you can use to make decisions. With these absorbance data, you also have a very easy path to get to molar extinction coefficient, and solve that for your own in-house drug linker molecule. In this case, what we're doing is running a simple trastuzumab emtansine read by ADC decode, getting an absorbance value at whatever wavelength we want, and then combining it with an average DAR value taken from something like HIC or mass spec. And then simple division will actually get us to our molar extinction coefficient. So now that we've solved this problem, it's solved for good, and we can continue to plug that molar extinction coefficient into into Stunner software anytime we're using an emtansine drug linker, and that will help us quantify and get to DAR for all those ADCs we're working with. Lastly, I did mention DLS at the start of this ADC section. Here's the DLS results for each of those 3 trastuzumab derivatives, and you can see that for emtansine and vedotin, sizes are very monodispersed and peaks are very sharp. However, for trastuzumab deruxtecan, we're starting to see a little bit of a broader distribution, which indicates that we have maybe some aggregation going on, and this is a molecule that we might want to either purify further or try out other buffers, or maybe start over again depending on how sensitive our next assay or process step is to aggregation. That's the importance of getting both UV-Vis and DLS information from ADCs at the same time, is that ADCs have a higher propensity to aggregate because of those hydrophobic drug linkers present on the molecules, so checking for that is critical before you use your ADCs. Here we're looking at a similar kind of experiment where we've stored a ADC over long periods of time, and again, like we saw earlier, on day 1 our intensity and mass distributions show one nice monodispersed peak, but on day 7 after storage we could see that we're starting to get large particle formation present, even though it's a small percentage of the mass. So that's ADCs, but really nowadays there's antibody anything conjugates. So I wanted to talk about one more class of molecule, antibody oligoconjugates. When you're reading an AOC by UV-Vis, the result of that is going to be a simple combination of the antibody spectra plus the oligo spectra, and that gets you to the total antibody oligoconjugate spectra. For Stunner, when you have that antibody oligoconjugate spectra, unmixing it or deconvoluting it into its component oligo and antibody parts is actually quite easy, because those oligo and antibody spectra can be determined from their sequences ab initio, so you're ready to go and analyze any AOC that you want. Here's a look at what AOCs look like by UV-Vis and DLS on Stunner. In this case, they're mock AOCs made by mixing an antibody with a 49 nucleotide aptamer. And we're doing this at 2 DARs. And you can see by the UV-Vis result, where we're overlaying each of these quadruplicate reads, we again have very precise quantification data and very precise DLS reads. And to analyze those UV-Vis results, we'll use the ADC quant application with an antibody oligo analyte. And we can take the total absorbance, shown by the black line of both of these AOC samples, and break it down into its underlying protein component in blue and oligo component in green. And then the residual error left over from the fit is shown by the yellow line. These reads can be used to quantify the antibody concentration, the oligo concentration, and the DAR immediately. And you can see exactly how precise all 3 metrics are by checking out the error bars. And in this case, all of the percent CVs were within 1.6%. This is all done automatically, both the ADC and the AOC quantification by Stunner software. So the moment that you open it up, you can see concentration, DAR, and sizing information, and results gathered in just about a minute per sample. So here we're looking at 16 ADCs gathered in 10 minutes of a total read. As I mentioned before, if you're looking to max out your throughput, Stunner is compatible with robotic automation for both liquid handling and plate loading. We have an API software package available to seamlessly integrate with many types of lab automation robot systems. And that's how Stunner gives you an all-in-one biophysical readout on your proteins, peptides, AOCs, and ADCs, so you understand sizing and aggregation, protein quant, and average DAR in a simple read from using only 2 microliters of sample. And hopefully, when you've got everything under control, you can really start to harvest some beautiful biologics.
Thank you so much, Kevin. That was a really fun, fantastic, and insightful talk. And we appreciate you sharing your expertise with us today. I'm now moving on into the Q&A session. So as a reminder to our audience, if you want to submit a question to our speaker, please enter your question into the box to the side of the live stream player and click send. We'll answer as many questions as possible during the time available. I can see we already have some questions submitted, so I will move straight on to these questions now. The first question we have is, how long does Stunner take to perform measurements?
So I usually think about this in terms of a total plate of measurements. So it can get through 96 samples for UV-Vis in about 10 minutes. And if you want to add on DLS for sizing information, it takes about 45 seconds or a minute per sample. So that means you'll be done in somewhere between an hour, hour and a half. Depends a little bit on your sample quality. But that will get you all the answers you need on sizing and aggregation, or sizing, aggregation, and quantification.
Great, thank you. And what is the size range that DLS on Stunner can quantify?
So the broad size range is between 0.3 nanometers and 1,000 nanometers. So that puts everything that are every biomolecule that we're working with squarely within that range. It makes it great for proteins, viruses, LNPs, things like that.
Great, thank you. Another question that just came in: how does Stunner compare to Dynapro Plate Reader 3 from Wyatt Technology?
Yeah, so this is Stunner and Wyatt Dynapro Plate Reader often get compared because they're both plate-based DLS systems. Stunner operates using a much smaller sample volume, only needing 2 microliters of sample. And then at that sample volume is more sensitive in terms of concentration than the Wyatt. And then Stunner also adds on UV-Vis to do a wide variety of quantification for biomolecules, and it has advanced UV-Vis applications to look at things like DAR or contaminant analysis.
Great, that's really good to know. Thank you. Can I measure concentrated antibody samples on Stunner?
Yes. So we can read up to around 275 mg per mil for average proteins. That's limited only by the 275 OD limit for UV-Vis on Stunner. For DLS, there's not really an upper limit. In that case, you only have to be concerned about viscosity, where samples can go up to 40 centipoise in viscosity and still be read.
Great. And the follow-up question is, what is the lowest concentration Stunner can read?
Oh yeah, makes sense. We went from highest to lowest. So for the lowest limit of concentration, you can go to about 0.03 milligram per mil for, again, a generic protein. If you're looking at using, say, for example, the ADC decode application that I talked about for some of the presentation, then our recommended minimum around there is about 1 OD at A280, perhaps 1 mg per mil. And that really just depends on getting enough signal from both your protein and your drug linker present in your read.
Awesome, thank you. And you said Stunner needs 2 microliters to run, but what's the dead volume?
So that's the nice thing about the microfluidics. It's a 2 microliter sample that you pipette in there. That's it. There's no additional dead volume or priming or anything like that. It's just, set your pipetter to 2 and go.
Awesome. Do Stunner's applications work for other conjugates?
Yes. So the only limit around, let's say, for example, the ADC decode application is that one component of a conjugate needs to be protein and one component needs to be not a protein. So we've used this with dye-conjugated proteins as well, like looking at QC before running flow cytometry. And we're always expanding our data set and continuing to look for more examples.
Great. And can this work on existing Stunners?
So any Stunner made since January 2024. Earlier versions also have access to the kind of old school DAR method, where you calculate drug antibody ratio from user input molar extinction coefficients. But the newer ADC decode algorithms require the newer software and hardware platform available since 2024.
Awesome. Thank you. The next question, can unused wells on the plate be used at later times, or is the plate single use?
Yeah, so I usually say this as normal plate law applies. If I use well A1, I can't use well A1 again, but all the other 95 wells are totally good. I can use them whenever.
Awesome. Can this be used to measure lipid nanoparticles aggregates and encapsulation percent changes during storage?
Yes. So for LNPs, the DLS on Stunner works just like it does on its sister product, Stunner AF, where we've added fluorescence. So checking out size and aggregation for LNPs on Stunner or Stunner AF with fluorescence is perfectly great. And if you do go for Stunner AF, where we've added fluorescence, we have made a suite of applications for LNP encapsulation efficiency that pairs up with RiboGreen to take a look at everything that you need on your LNP sample when trying to screen different formulations in production settings.
Awesome, thank you. The next question is, does Stunner software support 21C FRP 11 compliance?
Yeah, so we have a additional 21 CFR Part 11 license that you can add on to Stunner software, kind of thing where you enter in a code and you're with the dongle and you're ready to go, and it locks down the software in a very nice, elegant way that gives you all of the sort of password and audit tracking and signatures that you'd expect in a 21 CFR Part 11 validated workflow.
Sounds great. I'm just going through the chat to see if we answered all the questions. Okay, it seems we have another question. So next data and presentation, what are Stunner's protein size upper limitations in kilodaltons for a confident assay run?
Yeah, so when you go to 1,000 nanometers, you're talking, gigadaltons. So it's way up there. I would say a typical antibody, it's going to be about 150 kilodaltons. That will run about 11 nanometers by Z average size on Stunner. So you can go much, much larger. Even if, say, for example, AAV, that's going to run, by memory, somewhere in the 4 to 6 megadalton range. And even that's only at 30 nanometers in diameter. So the molecular weight you can go up to is huge. And then I usually think about it in terms of diameter. So using proteins and being usually between 5 nanometers and 30 nanometers, that's no problem for Stunner.
Awesome, thank you. That's really good to know. Let's just give it a bit moment for the questions to come in. All right, it seems that all the questions we have for today, and thank you so much for joining us, and that brings up to the end of the session. However, any questions that we didn't have time to get to will be answered offline as soon as possible. The webinar will now be made available on demand, and you can access the recording using the same link you used today. We'll also make sure any questions submitted on demand are passed along to the speaker. A certificate of attendance will also be sent via email to everyone who attended today's session. That just leaves me to say thanks again to our speaker, Kevin, and to everyone in the audience. We will see you again soon. Goodbye.